This is Relevance in the Wild, and I'm Daniel. The first thing that I can get out of the box is I hope that everybody has fuel after the lunch. Nobody just passes out or anything, and we can get through this. There are a couple of things that I wanted to point out before we get started, and especially after going and seeing all the presentations that we had throughout the last 2 days. And is that I'm not going to speak about anything related to machine learning. I'm not going to do any deep dive into some advanced feature in Solar, or actually, for that matter, something that is very new. So I'm going to mostly speak about all the tools that we have had in Solar for a really long time, hopefully in a very pedagogic way, so we get to learn something, and hopefully we can take something from there and either improve the practices that we have today, or get something to improve and to some ideas to apply on our different cases. And this is the agenda. So firstly, I'm going to speak a little about relevance. Then I'm going to speak about relevance within a field. Then we are going to expand it throughout fields. We're going to see how we evaluate that. And then we are actually going to get to the guts and speak about the real cases. So a little about me. I'm from Findwise, which is based in Stockholm. I have actually, mostly I work in implementation projects. So I'm mostly a Solar user. And either I implement the integration with Solar, we configure Solar, we do a lot of things. And throughout the last 5 years, for example, that I have been working with Solar, since we work in a lot of different small projects, we had a lot of experience on a wide ranges of cases. So I have worked in over a dozen of projects, and at the same time, I'm one of the people that holds the courses in Europe. So I have run a lot of iterations over the Solar courses in Europe. About my company, it's mostly just a consultancy company, and we focus on search on a wide range of expertise. We work with a lot of different platforms, and at the same time, we work not only with the technical side of things, but at the same helping business to realize the need for search and actually handle the information that they have. When speaking about relevance, I started checking the dictionaries, and there was a really funny evolution of the term between the different dictionaries. Some of them were just speaking about, okay, give me what I need. Then there were some definitions, like the Cambridge one, that actually added a little more emphasis on the context of things. So it is different for a person or another person. And then I was really surprised to actually see that there is even definitions, specifically scope to the case of information retrieval. And that's the one that we are going to speak about today. In a general way, when we speak about relevance within a big set of information, we can go to the set theory that how many of the relevance information are we getting? And we get to the typical measures of precision and recall. If we want to get all the information that we retrieve is relevant, then we are getting a really good precision. When we actually extract all the somehow relevant information within the full set of information, then we are increasing the recall. And that's always a balance that we have to even out. And when we are getting a lot of information, we are going to improve our recall, but the precision is probably going to be damaged by that. But that only is able to measure the relevance within a set of information. It doesn't actually evaluate the relevance of each of the individual documents within our information set. So if we go a little deeper and we say, okay, we got this set of documents as our relevant documents, what do we do with them? And something that is very important is to decide how we want to sort them. So Solar has the capability of saying, okay, I want to sort by this field or another field, and that can be text, alphanumerical order, or numerical value, or a date, or whatever of that side. But the thing that we actually do, or is done by default, and we always are going to try to strive for, is to use a similarity score to actually sort the documents according to their relevance. And how do we calculate that score? Well, that's the similarity score, and what we are usually going to do is we are going to evaluate how well a query matches a specific field. So now when we are speaking about similarity and the score, we're speaking about how well a query matches in a specific field, within a field only. And there we have all the different implementations that are available. There are some that are a little more classical, like TF-IDF. We have the little more advanced ones, like BM25 that we're going to speak about today. And we have a little simple ones and some wrappers to be able to actually configure your own similarity. But actually, behind the scenes, we are always going to use the same parameters when calculating a similarity score. We are going to use, obviously, the term frequency. We're going to check how many times does this term in the query appear in our specific field. And obviously, usually, we're going to use it as a direct relation with the similarity. So if we have a higher term frequency, we're going to have a higher similarity score. On the other hand of things, we have the document frequency. The document frequency is how many times does a term appear throughout the whole set of documents. When this is very high, meaning that all the documents have at least one instance of that term, that is probably a very clear sign that that term doesn't hold any semantical importance, or it doesn't really hold any kind of entropy. It doesn't matter, simple put. So when we aggregate all the different terms in the query, that one is going to have a very high document frequency. We are going to calculate the inverted document frequency. And if the term appears in a lot of documents, we are going to say, OK, this one is less important than whatever other more specific term that we have on our query. Then we have a little more parameters, and they are used in a little different ways depending on the similarity score that we are using. But the first one is the field norm. Depending on how long our field is, probably the term frequency is not going to affect our relevance as much. Obviously, a term appearance in a book is not going to be as important as a term appearance on a title of the book. So we apply that to kind of measure down the term frequency. And then we have the coordinator factor. Because we have a long set, well, we can have one or more terms in our query, we have to aggregate the score from all of them. And to be able to do that in a reasonable way, we have to normalize them together when we aggregate them. And that's what the coordinator factor will be. So in a more specific way, and we go to the math part of things, when we have the classical information retrieval score similarity, we have TF-IDF that just uses all the different parameters that I mentioned. Actually, the norm you can get out because it doesn't really depend on the term. It just depends on the field that we are looking into. And this was the default score that we had in versions previous to 6. But it's a really good, simple example to see all the different parameters that we have available and how we use them to calculate a reasonably good similarity score for calculating how relevant a query is for a field. If we actually go deeper into each of the different parameters, we are not just taking them out of the box. We are normalizing all of them. So for example, to be able to handle the term frequency without going skyrocket high and kind of allowing people to hack into our relevance model, we are decreasing the effect that it has as it grows. The same thing goes for the inverted document frequency. We are going to invert the classical document frequency, and we are going to apply a logarithm over it. And to be able to have reasonable sizes, we are going to add a 1 over it so that it goes from 0 to something and not from -1 to something. We really don't want to start adding negative numbers in our multiplications. When it comes to the length, again, we want the length to affect negatively on the score, so we use the invert value of it, and we actually square it. But that was before 6. Now we are speaking about the present, and this is some kind of a magical thing, and if you Google BM25, you actually can get some kind of area gas monitor machine, but that's not the one that we are speaking about. If you're interested in piercings, you also can find the store that actually gives you stuff. And if you are a little more hardcore, you can get a Soviet rocket launcher that is called VN25. So if you actually want to look for information about it, add Okapi before it. And then you're going to get actual relevant results about VN25, and you're going to find that in the end, behind all the scenes, it uses the same parameters that we had in TF-IDF. But the difference is, on the theoretical side, is just that it calculates things on a probability side, in a probability way. So it's going to try to figure out how high is the probability of the field to be relevant against how probable it is that it is not relevant. And there is a really nice academic paper that explains all the derivatives from that initial formula that I just mentioned to actually getting this. And it is really interesting from the mathematical side of things. But if we actually go on the more practical way of thinking, is that in a way we are using the same parameters. The only differences is that we have a couple of parameters, additional parameters, the K1 and the B, that allows us to tweak how things are affected. And we change how the length of the field affects the relevance. And the K1 parameter is going to affect how we allow the term frequency to affect the similarity, whereas the B parameter is going to allow us to tweak how important the length of the field is going to affect the similarity score. Again, the same way that we saw with TF-IDF, VN25 is not that simple. I actually added the normalizations in the formula that I showed you before, but the idea is it uses the typical compensations to be able to insert the parameters that I just mentioned that allow you to tweak how much the TF is affected with the K1 and how much the length of the field is affected with the B. They're down on the denominator of the length. Then we have the valid intervals for the different values, and I already showed you on the previous slide what the default values are. So actually, if you're in a case where your field length is kind of important to affect your similarity, you can increase the B a little bit. But again, take into account the relevant intervals that you can move the things. Usually, it's going to be most often between 0 and 1. Then we go to how do we configure this. And something that it's a little tricky is we actually need to use some kind of configuration template. So we have to upload a template with the schema template that will have this XML configuration that I'm showing you right there on the right to be able to initially configure it. There is a pending Jira case on Solar, so probably eventually we will have an API that will allow us to actually change the similarity. But since it will affect all the index, it will be something that will allow us to set it up at the beginning when we create a new collection. Then we actually can set up the different similarities depending on the field that we want to search. And this is kind of related to the thing that I mentioned before, that the similarity allows us to calculate how important a query is for a specific field. So you can have different types of calculation depending on the field. And one typical example that is very often found, if you research stuff, you just put a very simple similarity calculation for certain fields because you want to get a 1 or 0 or a very simple interval compared to the other fields that you have matches on text. And you would configure it like that. You just can add a field and select which similarity class you want to have. And then obviously with the class, you can add the parameters that we had in the end to be able to tweak it. When it comes to all the parameters that you have, these are the ones that we have in basic VN25. But there was a talk yesterday from Tom Bermans. It was pretty amazing about how we can actually add additional parameters on a custom similarity that we can calculate to be able to furthermore control how our curves look like when seeing how different the term frequency is affecting the similarity score. We can obviously write our own one. It's just a matter of extending classes. We can either take the base class that is available on Solar and expand it. And the only thing that we need to do, actually, is to rewrite the score function. And there we will have a couple of parameters that will allow us to retrieve the term frequency, all the parameters that I mentioned before. So it's just a matter of getting those parameters and playing around with them, like all the different similarity functions that are available. You can also extend the ones that are already implemented and try to build upon them. And that's the example of the presentation that we had yesterday. And obviously, write the factory that actually delivers the class contained in it. This is all that I had to say about searching within a field. But what happens when we actually want to search throughout different fields? Well, we are going to use Edismax, which is the Solar query parser. And what we are always going to have available for us is the field query fields parameter. And it is QF, no, not FQ. The idea is that we are going to be able to write a list of all the fields that we want to search into. And for each of them, we are going to calculate the score for our query. And then we are going to aggregate them together. The problem or the thing that you might not think about immediately when thinking about this is that you would expect that each of the matches will give you a score and everything will be together. That's not how it works. Actually, Edismax stands for Extended Disjunctive Maximum. So it will go through all the fields, it will calculate its score, and it will only take the biggest one. So it doesn't matter if you actually get matches on different fields, it's going to discard everything that is not the most important match. So if you get a match on 3 fields, it's not going to necessarily be more relevant than matching on an important field. But you can actually counter that effect and set the type parameter. The type parameter is just a factor that will be applied to all the discarded scores. So you can set it between 0 and 1. And if you were to put it at 1, you're actually going to get the scores throughout all the fields and getting them together. Then when selecting the fields, as you can see on the query fields parameter, you can actually add the caret sign and a boost number. That would be a number that will affect, in a factor way, how good a match in that field is. And then, over that, we have to decide how the matches throughout the different terms in our query are aggregated. And we can either decide to actually get all the matches for all the words. You can also decide to get only the matches that are matches on all the terms in your query, or you can use the minimum match parameter. That will allow you to set, okay, if we have a query with 3 words, I'm okay with getting the documents that match 2 of them. And there, it has a really expressive syntax that allows you to set up different intervals depending on how many terms each query has. One tricky thing about it, if you have any kind of analysis phase that manipulates the terms that are on a field, meaning stop words or synonym expansion, anything that adds or removes terms, you might be getting some unexpected results. Because if you're expanding synonyms, you're ending up with a query that has a lot of terms, and maybe your minimum match is going to actually try to expect to get matches on all the different synonyms for a thing. And it kind of counter-effects the fact that you are trying to expand a word with its synonyms. Over that, we have the debug parameters. So they will give you a marvelous, unreadable string that explains you everything. So usually you're going to want to either take it automatically and display it in your application, or to try to format it in a different way. But the good thing behind it is that it explains everything that we saw before. It will go through all the different parameters, and it will tell you, okay, we have this TF, we have this length on the field, we have this inverse, the document frequency. It even tells you all the coordinator factors and so on. And it tells you how the score was calculated. For example, here I search for book in the underscore text field. I didn't even look for different fields. And it tells you all the different parameters of the BM25, how they are aggregated or multiplied with the inverse document frequency, and in the end, how it is used for actually calculating the score of the document, because I only got a match on that field for that term. Then, and here we go to the most important part of what I wanted to show you, is all the tools that we have available to over a match affect our relevance score. And I'd really like to show this magic table because it points out all the specific differences between all the parameters that can affect the relevance. Usually, we're going to have our query that both controls how many matches we are getting and affects the score. Then we're going to have our filter query that is going to decrease the amount of results, but it's not going to touch the score. And this is the one that we are going to always want to use when doing not text queries, when doing interval queries, and we are going to want to atomize it so that it's as much independent from each other as possible, so we get all the advantages that we get from caching the results. Then we have the boost query, and that is just a parameter that looks pretty much like the query one. So it takes a query, a Lucene query syntax value in its parameter, and it will affect the score, but it will not actually filter out any of the results that we are getting. So that's the most common parameter that you're going to want to use if you want to apply a filter to improve relevance, but not actually filter out results. Then we have the boost function, which is exactly the same like the boost query, but instead of taking a query syntax, it's going to take a numerical value. And when it is calculated, it's going to be actually added to the general score as if it were a result from a term match. And it is going to be aggregated with the other queries with the coordinator factor. Then we have the most extreme of them, the one that is going to affect our relevance the most, and it's the boost parameter. It takes a numerical value as well. We can apply all our mathematical functions that are available in Java and in Solr. The difference is that it is aggregated as a factor. So wherever we get from all the previous ones, the query, the boost query, and the boost function is going all aggregated with the coordinator factor, is going to be multiplied by the boosts that we add with the boost parameter. And usually what you're going to want to do is you add whatever numerical value you want to, but you're always going to try to control the interval of possible values, either depending on the case, but mostly between 0 and 1. So you have a predictive, discrete interval of possible values. Then we go to how do we figure out what's the best thing that we can do with our things. And what we are going to always want to do is, OK, you're going to change your parameters, but you have to know if you're doing better or you're doing worse. So what you're going to want to do is change your stuff, evaluate it, see if it gets better, and then do another iteration. If you see that the results are worse, obviously you go back and you try to change something else. It gets pretty tricky because, as you saw, we have a lot of parameters. Each of the parameters can appear infinite amount of times in a way. So we have to be very careful of how each parameter affects each other, especially when it comes to the boost one compared to the other ones, because it's much more powerful. So what we are going to do is we are going to try to figure out to have some testing on our relevance. And these can be very advanced. You have seen a lot of talks that actually got the feedback from it much better. But what in an initial stage, if you have never done this, you would like to get some domain expert. You would get the person that actually knows what the information is about, someone that is very comfortable about all your information set. You're going to use your signals and your tracking of the user behavior to draw in all the most popular queries, and you're going to try to figure out what's the most relevant document for that one. And since that one is the set of queries or happenings that the users are going to experience the most, is a good starting place to actually evaluate and see how your changes on the relevance model affect the relevance, and especially those more common results. And then you're going to have some kind of automated script or whatever that runs those queries, and it tries to figure out in which position the expected result or the relevant result, and we always want usually one is going to come in. And usually we're going to obviously want that the result to come up on the top of the list. And when we run this, and we run this after changing something, we are going to see if the positions are getting down on the list or better on the list, if we want to keep the improvements that we did. And the results just look like this. You just have your query, wherever you're looking for, wherever you're expecting for, you run it, you see in which position the result appears, and you register it. And for each of the runs that you're going to do, you have the position, and you can compare them. Probably when you add some kind of boost on the year, you're going to have a better result for the second one, but you might lose something about the Edismax because maybe the documentation for Edismax is old or whatever. Also, as you advance your relevance model, not only the fields that we were speaking about, but you might have a lot of boosts based on the user information. You want to add all of those on your relevance testing. And usually when it comes to the user-specific information, it can be very tricky. So then you are going to have to need to register all the signals and use them to be able to track and evaluate those results. But it's just depending on what kind of level of ambition you have. And at the same time, you can actually use the users to calculate this for you. Whenever they search for something and they actually click on it, depending on the position that it is, it's enforcing actually telling you which is the expected document. And that will tell you in which position it is and what you can do about it. Depending on how popular that query is, you want to spend more time improving it or not. Obviously, with all the things that we saw through the last few days, especially with Fusion, you're going to have the possibility of leaving that to the machine. But there are like levels of complexity when it comes to this. At the same time, when we are using this kind of, we are selecting what's important for us to be able to evaluate our relevance model. There's a limit of how much can we evaluate. We are always going to discard a set of results, a set of things. So we really don't want to just optimize for our most best queries. We are going to then have a really bad relevance for our tail cases. So we really want to have a very wide list of cases and try to strive for improving the relevance throughout the whole set of information, not only the most popular queries. And then we go to the real thing, the real deal. And this is actually a very simplified set of recommendations, very common cases. How do we apply all the tools that we saw before to be able to gain some improvement in relevance using whatever we know about our domain? So there are actually a lot of ways that we could do this. There are a lot of different ways that we can normalize each of them. There are a lot of ways that we can configure them. For example, we can put if the parameters don't depend on a specific query and they are important for all our queries, we can actually pre-configure it as a default parameter in our query handler. On the other case, we can have the flexibility of sending it through with our query, but we are going to grow our query and have some kind of convoluted stuff. Obviously, when it comes to something that is depending on some contextual data, either the user or the time or whatever, we are going to want to use and send it with our query. And something that we always have to remember is to normalize them. We want to control how much they affect relevance, how much they affect each other, and have a discrete set of values that they can actually give to the relevance. Classical information model, we have some kind of CMS or wherever, and we want to search throughout a set of fields. We use the query fields parameter to actually search on all of them, but obviously our title is not going to be as important as our comments and so on. So we obviously, unique information like the ID, like some kind of marker of a specific document is going to need to get a really high boost, whereas information that actually is user-generated that we cannot trust that much, we're going to want to boost below 1. If we don't write any number, the default is 1. So the description will have the whatever score is getting by calculating that. Then, when we have a text field, we have a lot of different ways that we can analyze it. We can either have it as it is, don't have any kind of tokenization. We can tokenize it. We can stem it depending on the language. We can calculate the phonetic version of it. But all this analysis is going to actually allow the match to go on a very wide spectrum. If you actually search for a specific value, you're not going to get as many matches as if you search for a phonetic representation of that text. So what you're going to want to do, as usual, is you're going to have a lot of copies of the same information that go through different analysis stages, and each of them is going to have a different level of relevance. And we are going to use the more allowing ones to just give a little of relevance to affect it in a kind of fallback way. If we get a perfect match, we're going to want to get that one first. If we get a match on English, we just want to get it. And if we don't get any kind of match in the stem form, we are allowing the phonetic version to actually come up and fix our spelling problems. Then we have a synonym expansion. When we have a very specific set of information and the users have a very wide set of terms to determine something, we want to expand the searches. And this one is very simple to see whenever you're storing all the queries from the users. Very often they are writing something in a different way that our data set is written. So we always want to do some kind of synonym expansion on that field, and we are just going to add expansion on that things like vacation, to expand it to holiday, some kind of slang thing if the word has some specific kind of jargon, those kind of things. Then we have the document type tiering. Whenever we have a very varied types of documents, meaning we have a very big enterprise search that gets all the documents from collaboration sites, all the generally distribution information, the food menu, the vacation slides, all these things. Obviously, they are not as important as each other. Things like news are not as important as articles or distributed information. So each of the types can be tagged at index time with a number on how important they are. And whenever we actually make a query, we're going to use that field that has some numerical value of how important it is, and we are going to multiply it. Another alternative to do the same thing, if we don't want to preset whatever value they are going to have, and we have the flexibility of actually changing it through time without actually having to reindex everything, is to use the boost query. We just try to match the documents on a specific type, and we are going to apply a numerical boost on that one. But obviously, if you apply that on all your types, it's going to have a very big query. But at the same time, we have the flexibility of changing it from query to query or iterations. Then we have the date decay, a very classical thing. It just applies this reciprocal function that has an asymptotical size. So whenever a document gets older, it gets less relevant. And we are going to apply that relevance with the boost factor, so it actually is multiplied. And the usual value that it has, this magical 3.16 multiplied by a lot of tens, it's just the number of milliseconds that we have in a year. So that one will actually give half the relevance after a year has passed. You can use actually another number. Use the most reasonable way of decreasing the relevancy when it comes to date. I usually have seen that it is after a month or 3 months. So usually you're going to want to use a smaller decimal number there to actually get half of the initial relevance after a couple of months. And with that one, we will allow to decrease the relevance for all their information. And usually that's something that will affect things like news articles or like event information, that kind of thing. Then we have user customization. If we know something about our users, if we have an enterprise search that, for example, allows us to know what our users, where do they work, what department do they work for, whatever preferences they have, we have something that we can use when searching, when that user is searching. If we have an e-commerce site, then we probably have some kind of history about what that user has been searching for, what kind of categories or what kind of brands he has been looking for. So we can reuse that information as a boost query to partially affect our results and trying to lift up all the things that the user is probably going to like. Something very typical in an enterprise search thing, especially when it comes to the distribution information for a specific department, is that information about other departments is very often not important for a specific user. So you really want to lift up information that is either important for all the departments or for that user's department. Then we have, when searching for information that might have some location, then we can use that information to somehow sort stuff. And the typical case is when we have our restaurant repository or a list of shops. So maybe in our site, beside our catalog of products that we have a search for all our shops, physical shops. So we want the user to be able to search for stuff, but obviously we are going to want to recommend the things that are close to him. So we are going to actually have some kind of decay penalizing the shops that are far from the user. And obviously we are going to compensate that with the query of the user. Then, if we have any kind of rating or any kind of signals on how many documents have been seen, or any kind of reviews or scores on our information, we can actually use that to affect our results. And we are going to take the document's review score, or we are going to take how many views it got, and use it to make that document be more relevant. Obviously, like favorite things are more interesting to show. And then you can actually play around with it. If you have some kind of a score, but you don't have a lot of scores, maybe you don't want to use it. So you can have some conditional thing to require, I want to have at least 10 reviews or 100 reviews before I apply the review boost. And that's the second one. When it comes to e-commerce or selling information, or a catalog, we can just use all our information that we have in our catalog to modify the relevance of the stuff. We can decide to boost things that have a higher profit margin, which is just comparing the price and the cost. We can also encourage to get things that are very low on stock, or things that we have a lot of on stock and we want to get rid of. And that's just a matter of getting how many items do we have and either invert it or not. And we can also have campaign recommendations, so we can decide, okay, now we want to prioritize this kind of category. So we push it out on their search results, not only on our landing page. Then we can also combine all of this, but as I said, you have to normalize each of them so you can control the interval. You want to balance each other so they don't play out each other. And you really want to see, okay, you do a small change, you evaluate it, and you see if it performs better with your information. So whenever you're working with relevance, and this is something that, except for places like e-commerce that have a very, very important impact on whatever revenue you have, when speaking about the enterprise search, it's kind of an afterthought, but it really improves the user perception and improves productivity because they get the relevant information. Then we have seen all the tools that we can apply. You really want to work with our your signal, so store all the information that you can have about what it is search, what happens after a search, what does the user do, and where does the user belong to, either department, preferences within styles or brands or whatever. And you really want to evaluate things, so you actually can steadily improve your stuff and get forward and not get a chance to actually get things back. Or whatever you can do is actually run out something and let the users test it and do some A/B testing. But that's what I wanted to point out. That's all that I had. Thank you very much.